So in this video, we're going to talk about an example. We've actually already discussed the issue that f of x equals 1 over x is not uniformly continuous on the interval 0 to infinity, or on any domain for which 0 is a limit point of that domain. But we haven't proven it rigorously, and so I'm going to introduce you to a tool in this video for how you can do that. It's called the Sequential Criterion for the Absence of Uniform Continuity. And before we take a look at that criterion, I just want to remind you kind of what's going on here, why we know, or why we should have intuition that this function is not uniformly continuous on the interval 0 to infinity. So take a look here at this graph. What we notice is that if we're paying attention to this C1 value, we have a lot more wiggle room in terms of how far away we can walk from C1 and still guarantee that the piece of the function that sits above that neighborhood is going to stay inside the epsilon band. Whereas when I come over here to C2, notice that I can't walk very far if I want to guarantee my function is in there. And that just has to do with the fact that the rate of change of our function is approaching infinity there as we go towards 0, which means that there's going to be rapid change in your function values for a very small change in inputs. And so the high level here is we're saying that the issue is that 0 is a limit point of the domain 0 to infinity that we're working over. And as C goes to 0, the corresponding delta C is going to have to go to 0 as well. Therefore, there's no way to pick a minimum delta. That works for all C at once. So if I want to prove this precisely, to show that f is not uniformly continuous on a set A, I mean, a natural place to start would be to say, let's look at the negation of the definition. So I've written out here in the two columns, the left column has what it means for f to be uniformly continuous on A, and then the right column is just giving us the straight negation of that so that we know what it means to not be continuous. So a couple things to highlight here. First of all, we're going to be needing to find an epsilon neighborhood for which we cannot find this single delta that works all at once. But notice that that requires us that as we specify an arbitrary delta, we're going to have to come up with an example of x and y values that are in that delta neighborhood, but are too far apart in terms of their function values. There's actually a different way that we can think of this. Going back up to our intuition here, when we were saying, well, the issue here is that we've got a limit point of our domain, so namely 0, such that as the C values go toward that limit point, delta C's are going to go to 0. So it's kind of like, let's think about sequences. Is there a way for us to come up with, rather than always worrying about as I change delta, how do I pick an x and y? Why don't I just come up with a sequence of values, x and y, that are getting closer and closer together as n goes to infinity, but their function values are going to be too far apart. So that's going to be the premise of the sequential criterion for the absence of uniform continuity. And so I'm going to present that to you here. Okay, so here's the theorem. It has the most ridiculous name. This is not a name that you would necessarily see if you looked at a different textbook, so I'm not expecting you to memorize it, but it's called the sequential criterion for the absence of uniform continuity. And it's just a way for us to prove that a function is not uniformly continuous by using sequences instead of by using the negation of the definition. So here, notice that this is a theorem that is telling us how you show f is not uniformly continuous. It is an equivalent condition. This is an if and only if statement. what we are doing is we're going to essentially eliminate having to introduce this delta value. Instead, what we're going to say is that we have an epsilon and we have these two sequences in our domain where the distance between those inputs in the sequences is going to 0, meaning they're getting as close together as we want. So if someone gave me an arbitrary delta, I could make sure their distance was less than that delta value. So the inputs are getting closer and closer together, but notice the outputs are always too far away, no matter which two values you select from the sequence xn and the sequence yn. And so how do we use this? Some high-level knowledge here, I guess, about how you might want to approach it is that the key is to identify that location, that limit point of your domain, where the delta values are going to 0. Where the delta values are going to 0. And then from there, what you're going to try to do is come up with two sequences that are sort of going toward that location. And that's going to be how you come up with an example that will satisfy the sequential criterion. So the idea is identify the limit point P of A such that as C goes toward P, delta C is going to go to 0. And then pick xn and yn in your domain such that xn goes to P and yn goes to P. The reason why we do that is because if you have two sequences that are approaching the same place, then the difference of those two sequences must be going to 0. That's the algebraic limit theorem. So by the ALT, if I look at xn minus yn as a sequence, that has to go to P minus P, which is 0. So what that's really saying is that these magnitudes of the difference, since the sequence itself is going to 0, the magnitudes are going to 0 as well. But you want to be able to say that when you plug them in, you're greater than or equal, to some specific number, epsilon, that you'll have to identify. And so here the key to coming up with your example is, first of all, identifying that location where the delta values are shrinking because of the rapid change of your function, for example. And then not only do you need sequences that are going toward that point, you need two different sequences. You obviously don't want to use the same one, otherwise you're not going to get this function value condition because that'll just be 0. But the other thing is you want to pick not only two sequences that go toward that problem location, but they also evaluate nicely in your function. So depending upon what you're working with, that might say that one sequence is better than another. So for example, if you were dealing with a trig function, you might want to make sure you're working with sequences that not only go to the point P, but also evaluate on the unit circle, for example. So choose xn and yn such that they evaluate nicely. In F. So let's go back to our original problem. So we're back to our example. So here we are proving the claim f of x equals 1 over x is not uniformly continuous on the interval 0 to infinity. And we already know that for us, the issue that we get is 0. That's our p-value. So we want to pick xn and yn that are sequences of positive numbers because they need to be in the domain that we're considering, such that xn and yn both go to 0. And we also want to make sure that these evaluate nicely in our function. Now our function is 1 over x. Whenever you're looking for sequences that go to 0, you should always be sort of considering the prototypical sequences that we have. And so 1 over n is a nice prototypical sequence that goes to 0. And if I plug that into the function 1 over x, it inverts and just an n comes out. So it does evaluate nicely. So we can say, okay, one of our sequences is going to be 1 over n. Evaluates nicely and approaches 0. Then we need to adapt that sequence somehow to change it to a new one, to pick one for yn. And for me, I think the easiest way to do that in this problem is to just change the index of the sequence. So just shift it by 1. But what we want to check before we bother, writing up our proof is we want to make sure that when we go and we look at the difference of this function, we can actually guarantee it's always greater than or equal to some positive epsilon value. So I'm going to plug this in. When I do that, so I'm getting 1 over n minus 1 over n plus 1. So that flips, and I'm just doing n minus n plus 1, and notice that if I take that absolute value, I get the number 1. Well, that's awesome, because that's going to be greater than or equal to epsilon for any epsilon that we pick to satisfy that condition. So as long as I pick an epsilon that's less than or equal to 1, we're good to go. Some people might, make the suggestion of using like 1 over n squared as your second sequence, but notice then your difference that you would get when you're looking at your function values would be like n minus n squared, and that might take a little bit more work to try to find a single positive number that's always gonna be less than or equal to that. So here using a shift was good because it kept the order of our n's the same in our difference. So then we just write up our proof. And we're just going to follow the sequential criterion. So the sequential criterion says I need to say there exists an epsilon. So I'm going to let epsilon equal 1/2, or any epsilon greater than 0, such that epsilon is less than or equal to 1. And then I need to introduce my two sequences. So I'm going to let xn be 1 over n. And yn be 1 over n plus 1 for all n in the natural numbers. I need to note that I have made a good choice here. Xn and yn are both contained in my domain, which is the positive reals. And then because xn goes to 0 and yn goes to 0, by the ALT, if I look at xn minus yn, I look at their difference in absolute value, that's going to have to go to 0 minus 0, which is 0. What I'm doing here, the reason why I'm doing this is because notice that the conditions here, I have to show two things. Once I introduce my sequences, I need to show that the difference of the input values in your sequence is going to 0, and then I need to evaluate the function and show that those values are too far apart. But if I look at f of xn minus f of yn, that's just going to be what we wrote up earlier. So substituting into our function 1 over x, that's really n minus n plus 1, which is 1, and that's strictly greater than 1/2, which is our epsilon value. So by the sequential criterion for absence of uniform continuity, Man, that is a long theorem name. F is not uniformly continuous on the set 0 to infinity. And so that's an example of how you can prove rigorously that a function fails to be uniformly continuous on a set. And notice that the way you construct your example is built from the intuition that you have for why you're deciding that it's not uniformly continuous in the first place.